Hello students, in this video we begin our discussion of positive definite or positive semi-definite matrices or operators. Let's let T map a finite dimensional vector space into a finite dimensional vector space V. So here V is a finite dimensional inner product space. Let's assume it's a real inner product space too, okay? All right, be self-adjoint. In other words, T is equal to T star. T is equal to T star. In the matrix case, this will be A is equal to A transpose for a real matrix over here, right? So A is equal to A transpose. Then we say, so the implicit assumption is that these things are automatically self-adjoint, right? I need this assumption to make sure I can make proper sense out of square rooting numbers. We say that T is positive semi-definite if the inner product of TV with V is greater than or equal to 0 for all V in the vector space V, for all V in the vector space V, right? And so, of course, I want to figure out different criterion for matrices to be positive semi-definite. They play a very important role in optimization problems. So here's a proposition. So proposition, any one of the following is an equivalence definition of T being positive semi-definite. Okay, so let's talk about these criterion over here. So I have 1. T is just ordinary positive semi-definite. In the sense that TV, V is always greater than or equal to 0, right? 2 is that the spectrum of T, the collection of eigenvalues, are non-negative, like so. 3, T has a unique positive semi-definite square root. And finally, 4 is I can write T as, let's call it A star A for some A. Okay, like that. So those are 4 different ways to think about being positive semi-definite, right? This in some sense says that T is a square of something. This says that T is a square of something. This says the eigenvalues are squares of something. And this is a quadratic relationship. So there's in some sense an embedded notion of their T being a square in some generalized sense, okay? So let's prove this theorem. So how do we go about the proof? So proof, all these inclusions are relatively straightforward. So let's do them slowly. How does 1 imply 2? Well, if T is positive semi-definite, let V be an eigenvector. Okay, with eigenvalue lambda. Then what can I say? Then, okie doke. Then lambda times the length of V squared is just going to be lambda V with V. Of course, lambda V is just going to be TV, so this is going to be TV with V, right? And by assumption, we know that's greater than or equal to 0. Now, of course, the norm is greater than or equal to 0, and this is greater than or equal to 0, so lambda is greater than or equal to 0, okay? And that implies that sigma of T is contained over here. Great. Let's do 2 implies 3. Okay. All right, that T has a unique positive semi-definite square root. So of course I can diagonalize T. So if T has matrix A, T has matrix A with respect to an orthonormal basis, of course, then I can diagonalize it because it's positive, because I can diagonalize it. The eigenvalues by assumption are not negative, so I can write the matrix representation as P, some invertible matrix over here. In fact, it's going to be, or I can orthogonally diagonalize it actually, and then D and then P transpose, because P is going to be an orthogonal thing. And I can look at this matrix over here, consider the matrix over here B, which is going to be P, then square root of the diagonal matrix, P transpose. Now what do I mean by square root of the diagonal matrix? If D was just diagonal of lambda 1 through lambda n, then root D I'm going to define to be diagonal of lambda 1 square rooted through lambda n square rooted, right? And that makes perfect sense. I'm going to choose the positive square roots. So this, of course, so I can clearly check, then it's clear that b squared in this case is equal to a by standard arguments. So it is a square root, it's unique, and all of it, it's positive semi-definite because the eigenvalues of b are all chosen to be non-negative numbers. So that implies 2 implies 3. How do we get 3 implies 4? Well, how am I going to do that? Well, if it has a square root, I can write t as what? So t is therefore equal to what? Is equal to, let's say, s squared, right? But s is also what? S is positive, is a square root, it's positive semi-definite, and it's going to be what? It's positive semi-definite, so it's automatically self-adjoint. So for this case here, s star is equal to s by self-adjointness, so t is equal to s star, s, and that gives us that 4 implies this. And then finally, how do we get the last inclusion? The last inclusion, 4 implies 1, to show that they're all the same. 4 implies 1. How do I do that? Well, if t is equal to a star a, is equal to a star a, then what will t, v, v look like for any vector v? It's going to look like a star a, v, v, like that, right? And then this, of course, I'll pass the adjoint to the other side. This is just a, v with a, v, by passing the adjoint over, and that's greater than or equal to 0, because that's just the norm of AV quantity squared. That's just the norm of AV quantity squared. Right, so in other words, this gives me 4 distinct ways of thinking about what it means for an operator or matrix to be positive semi-definite. To be positive semi-definite, all the eigenvalues have to be non-negative numbers, or you can find the square root of that operator, or you can decompose that operator into of the form a star a. Of course, anything that looks like a star a is clearly going to be what? It's clearly going to be a symmetric expression, because if I do the adjoint of this, I get the same exact form, and then it's always going to be positive definite. So in other words, any of these representations are going to give me a criterion for being positive semi-definite. And we're going to see in further videos that we can use this to construct a polar decomposition of any matrix. Because in some sense, what this is giving me is that if I take this positive definite part, I should be able to say that that in some sense is like in some sense the amount that the operator is going to stretch out up to the square root of that thing over there. So we're going to use this decomposition carefully in further videos to understand the overall structure and polar decompositions and singular value decompositions. Thank you very much.